Welcome to Blockchains. In this episode, we're going to look at encryption, blockchains, nodes, and the rest of the ecosystem. By the end of this lesson, you'll know exactly how blockchains work and how all the different pieces tie in together. So first, let's get started with encryption. This is a very simplified way of explaining encryption, but it should give you a good understanding of how it works. So let's say you're in a classroom and you're at the back of the class, your friend is at the front of the class, and you want to pass a message to them. But you want to make sure that nobody in between you guys, when you're passing the message, is able to read that message. So you would have to encrypt it. How would you do that? The first thing you need to do is write down your encrypted message, right? So for us, our encrypted message says, "Hold my beer." Next, you would have to create a encryption key. So the encryption key is very simple. You just have another piece of paper, and on that paper you write A equals whatever you want. And then, so for us, we'll write A equals O, B equals 2, C equals D, D equals 8, and so on and so forth. These are just randomly chosen. Then you take your encryption key and you look at your original message and you rewrite that message. So every time you see an A, you would replace it with an O. Every time you see a B, you replace it with a 2. Every time you see a C, you replace it with a D. So by the end of the message, it should look something like this. This entire string of letters and numbers now is an encrypted message, and it looks like gibberish, right? Anybody that looks at this wouldn't understand what it means. This is also known as a hash. We'll get into what a hash is further on in the episode. So after you have your encrypted message, you take your encryption key and you also pass that to your friend. And these are sent in two separate transactions, right? So that you don't want to pair your encrypted message with the encryption key because then it's pointless. So you have to send it separately. But after your friend has the encrypted message and the encryption key, then they can decode this message so that they can read what your message was. And that's how encryption works. So what is a blockchain? Blockchains are the underlying technology that all cryptocurrencies are built on. There are three key components that make up a blockchain. It's cryptography, blocks, and nodes. So cryptography is basically encryption. It's what we just discussed. In a blockchain, cryptography is mainly used to protect the user's privacy and transaction information to ensure data consistency. We'll talk about data consistency in a minute, but for our purposes here, the only thing we need to focus on is it will protect a user's privacy and transaction information. Next, we have a block. A block is a container where transaction data can be stored. Multiple blocks are chained together to form a blockchain. If a blockchain is like an Excel file, then each block is like an individual cell within that Excel file, right? So you have a cell that is just a container for information, and that cell is inside of an Excel file, and an Excel file is just a bunch of cells that are grouped together. So you store all of the transaction data inside a block, and then once that block is full, it gets chained to all the other blocks. And the entire chain of blocks is called a blockchain. And finally, we have nodes. A node is just a computer. It's what blockchains run on. So an example of this would be your iPhone and the operating system that runs on it. It's called iOS, right? If you have a Samsung phone, it's running on Android. And so it's the same way with blockchains. So iPhones run on iOS, Samsung runs on Android, nodes run blockchains. A blockchain is made out of hundreds of blocks, thousands of blocks. And each block contains three pieces of information. It contains data, hash of the current block, and hash of the previous block. So data is basically the transaction information. On the Bitcoin blockchain, it's basically each piece of data is who the currency is from, who is going to, and the amount, right? So Stephanie sent 1 Bitcoin to Anna, and that would be one transaction. Next, you have hash of the current block. So the hash of the current block is like a fingerprint of all the transactions within that block. So you have a bunch of transactions that go in the block, they get locked, and then it generates a hash. This is like a fingerprint of that block. Also included in the block is a hash of the previous block. And so the hash of this block gets stored in the block before it, and so on and so forth. This is how they get chained together. Let's look at this in more detail. So this is the first block. The first block of every blockchain is called the Genesis block. It's a special block because it doesn't have a previous hash, right? It's all zeros because this is the first block. So let's say you have a bunch of transactions that go into here. This block gets encrypted. A new hash gets created. The second block takes the hash from the first block, adds it to all the transactions, and when this block is full, along with this hash, it gets encrypted, and then a new hash gets created, right? So if we look back at our encryption example, you have the transactions plus the previous hash, which gets encrypted with an encryption key, and now you have a new hash. And this goes on for the third block, and so on and so forth. And this is what the chain of blocks looks like. Another way to think about this is, let's say you put some important files in a vault, in a safe, and then you take a key to that safe. Then you take more important files and the key from your previous safe and lock it in a new safe. And then you take the key from that safe and you lock it in a new safe. And so if you ever want to get to the first safe, you would need to take the keys from all the previous safes to be able to access that. So let's say a hacker tries to inject fake transactions on block 3. If he changes anything, literally even one letter, then the entire hash of that block would change. And if the hash for block 3 changes, then it would also invalidate all the future blocks of that blockchain, right? Because if the hash changes for block 3, then it would also change for block 4 and 5 and so on and so forth. The servers that run the blockchain will know that this is a fraudulent transaction and just automatically throw away that entry. Next, let's look at how we store data. So this is Amazon's data center. It is 12 million square feet and it can power tens of thousands of computers. These computers are used by companies like Disney, Netflix, Airbnb, and NASA to host their data on the internet. Inside of each of these data centers, you have hundreds of server racks. These are just cabinets that hold computers and keep things tidy. And inside of those server racks, you have individual computers that are built specifically to process data. These aren't like the computers that you have at home. They're computers that they're not connected to any monitors, mice, or keyboards, and they're also very flat. They're built so that they can be put inside of server racks. So what would happen if someone were to attack this data center? If we blew up this data center, it would also kill all of the servers inside, right? That would mean that companies like Netflix, Disney, and anyone else that uses these servers also goes offline. This is very risky because it creates a central point of failure. We actually saw this a few years ago when Amazon Web Services went down for a few hours. Netflix went offline, Instagram went offline, a lot of the internet went offline because of Amazon servers going down. And Amazon provides a large part of hosting for the internet. So it's a big infrastructural juggernaut when it comes to hosting data online. So if centralized storage is so risky, how do we prevent against it, right? We would have to do decentralized storage. So instead of storing all of your data in a data center, blockchains store their data across thousands of computers around the world. These computers are known as nodes, and nodes are the same thing as servers. It's just a different name. Anyone is able to join the network permissionlessly. This means that you don't need to ask for approval to join or leave the network. And the network rewards people with cryptocurrency for joining and helping secure the network. The way that this works is you create a node, right? If you have a computer that you want to use as a dedicated node, you would have to set it up. There's certain amount of technical expertise that you need to set up a node. But once you set it up, you don't have to ask anybody's permission to join the Bitcoin network. You can join it whenever you want. You can leave whenever you want. So if a hacker tries to attack this network, and even if they gain control of some of these nodes, the network is going to slow down, but it's not going to completely go offline because other nodes will be able to continue processing transactions. The problem is if a hacker is able to gain control of 51% of the entire network. And if they do that, it's pretty much a catastrophic failure. That means that they own the entire blockchain and they can do whatever they want with the crypto on that blockchain. But this is extremely hard to do because all of the nodes are distributed across the world and there's no single point of failure. So you would have to essentially hack 51% of all the computers around the world that are supporting the Bitcoin network, which is impossible to do because you would have to find all of them around the world. It's just very highly unlikely. Every node has a copy of the blockchain on it. For a distributed system to work, you need a way to sync all of the individual nodes together. Right, so it's like imagine that you have a very large Excel file that's being shared with thousands of people around the world, and you need to make sure that everyone's copy is exactly the same. So the only way to do this is through a consensus algorithm. And there's two main types of consensus algorithms. There's proof of work and proof of stake. In proof of work, nodes compete with each other to solve a complex math problem. These nodes are also known as miners because they mine for the correct answer by randomly guessing it millions of times per minute. Right? This is a very resource-intensive task because the answer is guessed randomly. So if you have more guesses available to you, then you're more likely to be the first one to guess the right answer. Right? It's kind of like the lotto. If you have more tickets, you have a higher chance of winning. And it's very important to be the first one to guess the right answer because the first node to guess the answer broadcasts it to the rest of the network and the other nodes verify if that answer is correct. And if you're the one that has the correct answer, you get awarded Bitcoin. That's how it works for the Bitcoin blockchain with proof of work. These rewards get cut in half every 4 years. This is also known as the Bitcoin halvening. So if you've ever heard the word crypto miner, this is how it works. And this is how they make money. They operate hundreds of nodes in the hopes that they're the first ones to guess the answer correctly. And if they are, then they get awarded Bitcoin. What they do with that is they sell the Bitcoin to pay for their electricity and operating costs, and they keep the difference as profit. Next, we have proof of stake. This method is 99% more energy efficient than proof of work, which is basically the main criticism that most people see for Bitcoin. Right? A lot of people criticize Bitcoin because of the proof of work algorithm is so energy intensive. And so proof of stake helps alleviate that problem. The nodes in proof of work are known as validators. It's just a different name for the same thing. In proof of stake, validators lock up their crypto to participate in a network. Each blockchain has a minimum requirement to become a validator. On Ethereum, you need to lock up 32 ETH to be a validator. This is called staking. We'll get into staking further on into the course. Locking up your crypto is necessary so that the network can punish you if you behave badly. If your validator goes offline, the network will burn some of your staked crypto. If your validator tries to inject fake transactions or misbehave in any sort of way that is bad for the entire blockchain, your crypto starts getting burned. So this is how you get penalized for behaving badly, and it also incentivizes you to, do the right thing. This is called slashing. When your crypto gets burned, it's called slashing. Validators are chosen semi-randomly. They're not fully random, they're semi-random. And the way that this works is the network takes into account how much of your crypto you have staked and the amount of time you've been staking. So if you have a validator that you've been staking for a long time and you have a fairly large amount of crypto staked, then you have a higher chance of being the winner. That's because the network has a history of your trustworthiness and you have more to lose. So you're less likely to inject fake transactions or misbehave. The winning validator gets to collect the transaction fees from the blocks that it proposes. So all the transactions within this block pay a certain amount of fee to the nodes. And if you're the winning validator or node, then you collect these transaction fees. And this concludes our blockchain episode. There's 3 key components that you should get out of this. Number 1, you can lock a message with an encryption key to make sure it's unreadable to anyone else that doesn't have that key. This is how all passwords work. The password functions as your encryption and decryption key for all of your accounts. 2, blocks get chained together by taking transactions, the hash of the previous block, and then encrypting that entire block. This creates a new hash for the current block. Then you take that and you put it into the new block with more transactions, and that creates a new hash for that block. And that's how blocks get chained together. So it's like if you took your files, put them in a vault, and locked it with a key, then you took that key and put it in a new vault with new files and locked that vault, took that key, and then kept going on and on. So that's how blockchains are formed. And finally, nodes are the backbones of all blockchains. They keep a copy of the entire blockchain on them, and they keep that in sync with other nodes by using a consensus algorithm. In proof of work blockchains, the nodes are known as miners, and in proof of stake blockchains, the nodes are known as validators. And that's it for blockchains. I'll see you in the next lesson.